All right, so let's look at this ladder problem. The ladder question, first of all, I think most of the groups had at least some of the forces drawn right, if not all of them. So first we need to draw a free body diagram of all the forces acting on this ladder that's in equilibrium. Okay, so forces. Definitely the ladder has a mass that was given to you. And so it will have a gravitational force, and I'm going to call it FGL, where it's the gravitational force of the ladder, because the mass of the ladder was 12 kilograms, I believe. Then there is a painter on the ladder. We're going to treat that painter as a point mass that is applying truly a normal force to the ladder, but it would be equal to his weight. So overall, the weight that of the painter or the person, FG person, and we have a mass of the person. I think it was 55 kilograms. All right. Now, you're told that the wall is frictionless. And so, but the wall still applies a force. And if the wall is, I'm going to draw just a dotty dot dot line to represent the wall there. If that's the wall pushes and holds the ladder up with a force from a surface perpendicular. And we usually call that a normal force. And I'm going to call it normal wall. Okay. Then down here, the floor, and I'll put the floor here. There's a floor right there. The floor is doing two things. The floor is holding up the ladder with a normal force from the floor, as well as applying a frictional force to the bottom of the ladder, holding it from sliding. So, which way would the friction force need to be if this person is climbing the ladder? Towards the wall? So I'll draw this friction force, friction from, and it's going to be static because we don't want it to slip. That's the whole thing. And this will be the floor. All right. So far, so good? So those are all the forces acting on our ladder. Now, a couple of things we need to include. The angle. So I'm going to just sketch over here the ladder, the wall, the floor, and you were told the ladder has a length of 5 meters. The wall from the point of contact to the floor is 4 meters. And from the corner here, the intersection of the wall and the floor to where the ladder rests is 3 meters. So then this angle right here would be what? The inverse tan of theta would equal the inverse tan of 4/3, which is what? So that gives us a 53-degree here, which means that my other angle, and I'll call it phi would be what? Would be 37 degrees. Okay, so now I know the angles to the vertical are 37, and the angles to the horizontal are 53. So far, so good? Okay. So then with a color over here, angles to the horizontal are 53. Angles to the vertical are 37. Do you see that this is a vertical angle, 37? And this one would also be 37? And that this one is to the horizontal, so it would be 53. All right, so the next step is to then after we do our free body diagram, we need to sum the forces in the x direction. Now, if this ladder is in equilibrium, all the forces in the x direction are balanced. If we start at the top and we just look at the forces that are horizontal, there's a force normal wall that's pointing to the right, and there's a force friction static pointing to the left. So we'll have force normal wall minus force friction static floor. And those are Those must be balanced in order for it to not slip. That's just the way it has to be. Okay. Let's do the y direction. Now, y direction, up and down. We've got a normal force from the floor up, and we have the two weight forces down. So when I sum the forces in the y direction, they must also be balanced for this thing to be in equilibrium. So the normal force from the floor minus the gravitational force of the ladder minus the gravitational force on the person would equal 0. Now, the new piece to this is the fact that all these forces aren't acting at the same place. And if you climb this ladder, you're moving the weight of the person to a different position with respect to the pivot point on the floor, okay, the place where it might slide. And so we need to see we need to sum up all of the torque acting on the ladder and set it equal to 0. So let's do that. Now here's the thing, we need some distances. So if the length of the ladder is 5 meters, so the whole length of the ladder is 5 meters, then where is the gravitational force of the ladder applied? Yeah, that would be 2.5. So I'm drawing a very ugly bracket there. 2.5 meters. Now, the question tells us that the painter person is 3.5 meters. So I'm making my bracket. It's also going to make this thing look ugly. But 3.5 meters from the floor. So now I know where those two forces are applied. Now I want to pick a pivot point, a place where the net force or the net torque would be summed about. I am going... All right, so now let's sum the torque. And I'm going to pick a place that is convenient. So this is important because this isn't necessarily intuitive, okay? We want to ultimately find the coefficient of friction. And if you think back to what we learned first semester, the coefficient of friction is buried inside the force of friction. So that means that the force normal wall will equal force friction static from the floor. And what is the equation for the force of static friction? Yeah, so your mu static times force normal from the floor. And this would be force normal wall. Okay, now look at our our vertical equation here. Does the normal force that the floor applies to the ladder equal the weight of the ladder plus the weight of the painter? And we have those things. So look, that is this portion of my equation. And I can solve for that number and find it. Okay? But I don't have the normal force the wall has to apply to the ladder. That is this force right here. I need to find this one. Okay? Now, if I make my pivot point up here, then what's the distance, the force I need is from the pivot point? 0. So it's not even going to be in my torque equation. So how can I find it? Don't put the pivot point there. That's a good idea. All right. Now, if I put the pivot point at the center of mass, so right here, then I'll have a torque from the wall. I'll have a torque from the painter. I'll have a torque from the friction force and a torque from the floor. How many is that? That's 4. Okay. The other place I could put it is I could put the pivot point down here at the floor. If I put it at the floor, I will have a torque from the wall, I'll have a torque from the painter, and I'll have a torque from the ladder, but the two forces on the floor are at 0 distance. So how many torques will I have now? Which is less than 4. So that's probably the most convenient place for me to put the pivot point. So I would put the pivot point right here. So that's where we're going to sum all of our torques. Okay? So, here we go. Now, if you just look at the force the wall applies, and that was all you're looking at, and you don't care that it's a ladder, here's a pivot point, here's a rod, and here's a force. Which way would that force from the wall cause the ladder, cause the thing to rotate? Clockwise. All right. Now, just looking at the gravitational force or the weight of the painter, which way would that make the ladder turn? Counterclockwise. And what about the weight of the ladder itself? Counterclockwise. Have you ever propped something up and it fall down? Yeah. And when you prop the boards up around the room, like Grant has his propped up back there, sometimes I'll say, oh, you need to increase the normal force from the table, because then it would increase the friction force. So then it doesn't slide. Ha, yeah. All right, so these 3 forces then would apply a torque, but these 3 forces are mean, ugly forces to you today, and they're not perpendicular. We've got to find the perpendicular component of that force. We need the perpendicular component of the weight and the perpendicular component of the weight. Oh my goodness, it got messy. Okay? So we can do this. All right, so now let's sum the torque. So the normal force from the wall, actually let me change a color here. So when I sum the torque on the system about the floor, if I don't want it to rotate, if I don't want it to slip and slide, then the torque has to be balanced. So the force normal from the wall, the component, I need the opposite, right? I need this component right here. So opposite of the angle, sine of 53, and then where is that force? Well, the wall compared to the pivot point, which is going to be down here. 5 meters, that's right. The whole length of, I'll put P for pivot. I'll actually just spell out pivot. Here we go. Pivot. Nope. Watch friends. Okay, so then this would be 5. All right, then minus, why am I going to subtract the torque from the gravitational force of our painter? And that angle was 37 degrees. Remember, we went back and put all of our angles in? And whereas this one, he's at 3.5 meters from the pivot point or the floor. Then the weight of the ladder itself, so the gravitational force of the ladder, but it's not perpendicular. It's at an angle of 37 degrees to the ladder, but it's at 2.5 meters. Then all of that would equal 0. So this is the torque due to the normal force on the wall. This is the torque due to the painter. And this is the torque due to the ladder. Can we find the normal force from the wall at this point? I think so. I think we have enough information to solve for this unknown, which if we do, we can stick it back in up here. I believe if you rearrange and solve for the normal force applied by the wall, you will get 335 newtons. And then over here, if we're looking for the force normal from the floor, and we add up the weight of both the ladder and the painter, we'll get 670 newtons. I just M times G plus M times G. And then this is substituting M times G, sine 37, doing all the math out. So I'll leave that as an exercise for the student, so you can go back and check that. So then the force from the wall, the normal force from the wall, should be equal to the force of friction static from the floor. So I'm just repeating what we had written up there. So the normal force from the wall should be equal to mu static, and this would be the normal force from the floor. All right, so the mu static would be the force normal from the wall, which we just calculated, over the force normal from the floor, which we could also calculate. So 335 divided by 670, and that should give you about 0.5 as the coefficient of static friction. So now let's look at, we've got a pulley, a solid disc, and there was a 2 kilogram, which one was on the left? So this guy was 1 kilogram. The mass of our pulley disc is 0.25 kilograms, a quarter of a kilogram, and its radius is 2 centimeters. And then over here, there was another object hanging here, which was 2 kilograms. And we wanted to eventually find the acceleration of the system. So I gave you some hints. First thing we needed to do was draw the free body diagram. And I think most of you got those right. But now that we have a mass-full pulley, the tensions are different. Because you have to have a difference in tension to cause a difference in torque, and you have to have a difference in torque to cause the thing to revolve. Okay, you're not going to have an alpha if it's not an unbalanced torque. All right, so that is my 1 kilogram mass. My 2 kilogram mass was an FT2 and an FG2, and then I have the disc. And the disc has a couple of different forces acting on it. It definitely has its weight, and I'll call it FG3. And it definitely has some sort of FT3, a tension force holding it up. All right. And then this would be FT1 because that's the tension coming off the left side and attached to the 1 kilogram object. And then over here you've got your FT2, and that's the tension attached to the 2 kilogram object. So you guys had that drawn out nicely. Then it comes down to summing the forces. Now, the 1 kilogram mass, I believe, will go up when I release it. So I'm going to make the up direction positive for the 1 kilogram mass. Because the 2 kilogram mass is the big guy, I think that it's going to go down when I release it. And so I'm going to let down be the positive direction for that guy. And in order for this to go up and the 2 kilogram mass to go down, my pulley has to rotate this way. So I'm going to make clockwise positive. If I was being a much better teacher, I would have FT2 much longer than FT1, but then I have to have FG2 greater than FT2. It's got to be bigger, so I've got to have differentials there. And this guy right here, I'll just go ahead and make him look significantly smaller, like that. So then that shows that the net force on the 1 kilogram object is positive. The net force on the 2 kilogram object is negative. And then over here, I should really do the same thing and have that this FT2 over here equal but opposite to that length there. I'm just going to eyeball it something like this. And then, to make it even more fun, the total force FT3 has to be equal to all three of those. So it would be like, whoa, way up into this previous question. So those are more to scale. But very good question. I thought about it as I was drawing it, that I probably should draw them to scale, or at least relative to each other, to be a good model of how to do good stuff. What's up? All right, so now let's sum these things. So when I sum the forces in the y direction on the 1 kilogram object, it will be equal to m1 times a. The whole system is still going to have the same acceleration because it's still connected by the same rope. The problem is the rope has to have a differential or a different tensions in each side so that it can cause the rotation in the first place. Okay, so then we'll have Ft1 minus Fg1 is equal to m1a. The x direction is boring, and so I'm just going to omit it. For the m2, so my 2 kilogram mass is my m2. It would have the same acceleration. Again, they're all in the same system that's accelerating. So the forces on it would be the tension on it is not positive. I'll put the positive one first. The gravitational force on 2 minus the tension force on 2 would cause the mass 2 to accelerate. And then if you wanted to, because sometimes you might be asked, summing the forces on the pulley itself in the y direction would be balanced. The linear forces are balanced. Unless that pulley is falling out of the sky or rising up in an elevator, all the forces on the pulley, linear forces, are balanced. The pulley does not have a linear acceleration. It is not going to translate. It's going to rotate, but not translate. Just like mass 1 translates, it does not rotate. So you would have Ft3 minus Ft1 minus Ft2 minus Fg3 is equal to 0. So if we found all of our tensions, we could go back and figure out how strong does the string that hangs the pulley from the ceiling need to be, which is an extension question, I suppose. Now, the new part, really. We're going to sum the torque on the pulley. And let's just do it over here so we can see the pulley at the same time. So when I sum the torque on the pulley, and nope, it's not balanced, but I sum the torque, the pulley's mass, which is distributed all over the place, is going to accelerate rotationally. So there's an alpha. So then Ft2 is applied at a distance r, and Ft1 is also applied at a distance r, and both of those are perpendicular. We don't have to find a component. Aren't those both perpendicular to the radius? Like a teeter-totter? Awesome. So then that would equal I times alpha. So now I have like 3 equations and 3 unknowns, and it's a big, gigantic, ugly-looking thing, and you cry. No, you don't. You solve it. All right, so here we go. Do you see that we have an Ft2 and an Ft1 up here? Do you see that you have an Ft1 and an Ft2 here? So I can isolate Ft1 and isolate Ft2, which I didn't underline. I underlined the wrong one. Isolate Ft2, and then jam those back into that torque equation. That's the plan. Okay? So the physics is over. The algebra begins. So I'm going to take this guy over here, and would ft1 equal m1a plus, is fg1 the same thing as m1g? I'm going to make that substitution as I go. The gravitational force is mg. Okay. Then I'm going to take this one over here and let's ft2, would that be m2g minus m2a? All right, so now from our torque equation, I'll write it down again. ft2 times r minus ft1 times r was equal to I alpha. All right, so ft2 is this thing. So we're going to have an m2g minus m2a all times r minus ft1 is this thing right here. m1a plus m1g all times r is equal to I times alpha. Now, A is equal to R alpha. That's the way we can put these two accelerations together. The string is tangent to the circle, and so if you can find the tangent acceleration of the pulley disc, then you will have the acceleration of the rope. And the rope has the same acceleration as the hanging mass, because that's what's attached to the hanging mass. So we can make this connection here. And I actually like to make it this way. Alpha is equal to A over R. Can you dig it? All right. And the moment of inertia for a disk is 1/2 mr squared. All right, so I'm going to have m2g minus m2a all times r minus m1a plus m1g all times r is equal to 1/2. I'm going to call it m3 for my pulley, the radius of the pulley squared, times the linear acceleration of the edge of the pulley divided by r, the radius of the pulley. So this A right here is the same A here and here because it's the acceleration of the rope, and the rope is attached to the masses. All right, so now you need a lightsaber. All right, so this R here is the same as one of these. So one R cancels with one R there. And then R and R and R cancel out. So, oh my goodness, we're left with M2G minus M2A minus M1A. Don't forget to distribute your negative sign. Minus M1G is equal to 1/2 M3, that's the mass of the pulley, times A. Whoosh. So now M2G, that's the weight of the big guy, minus M1G, that's the weight of the small guy, is equal to 1/2 the mass of the pulley, because the moment of inertia of a pulley is 1/2 mr squared, okay? But plus, if I add over the M2 term, plus M1 if I add over the M1 term, all times A. Now can we solve for acceleration? Oh my goodness. Yay, science. All right, so 20 minus 10 divided by what that 1/2 of 0.25 plus 2 plus 1 is equal to A. And when I did this, I got an acceleration of 3.2 meters per second squared. We had a string wrapped around a disc, so kind of like a yo-yo. So here's our disc with a string wrapped around it. The mass of the yo-yo, what was the mass of this thing? Was it 1 kilogram? Yeah, it's like a yo-yo. Was it 1 kilogram? So 160 grams, and the radius I 0.025 meters. Okay, good. All right. So free body diagram looked great. So you have the disc, and there's a tension force on it at the edge, and there is a gravitational force on it at the center of mass. So that was good. Then when we sum the forces, and only the y direction because everything else is boring, is this thing going to accelerate vertically? Is it going to go from being up here to being down there later? Oh, yeah. Yes. So it is going to accelerate. Which way is it going to go, up or down? All right, so I'm going to let the down direction be the positive direction. And now, if this is unwinding, which way is the disc going to? It's going to have a clockwise rotation. Okay. So we got an FG that would be positive minus an FT would equal MA. And when I sum the torque, the whole thing is going to also have an acceleration. Again, the acceleration of, and this time, this is kind of cool because as this thing unwinds, the center is going to have an acceleration that is going to be equal to the acceleration of the edge because it's going to look like that as it falls down. Falls straight down, like the toilet. And when it hits the ground, it'll roll away. What's up? So this translational acceleration of this piece of the wheel is the same, is what I was getting at. The whole thing will have the same acceleration. So what's causing it to rotate? The reason why it spins is there is a tension force acting at the edge of it, and that would cause the I to alpha. So then FG minus MA would equal FT. And so then FG minus MA all times R, because I'm going to substitute it back in up here, would equal the moment of inertia times alpha. Now the gravitational force is M times G minus MA times R. The moment of inertia of a disk is 1/2 M R squared. And alpha can be related to A. Remember, A is equal to R alpha. Therefore, alpha is equal to A over R. So put in your A over R. And what do we see? This R can cancel with one of those. And then this one can cancel with that one. Because it's multiplied by every term on both sides. So then mg minus ma will equal 1/2 ma. So then mg is equal to 1/2 ma plus ma. And I can divide by m on both sides because it's one thing that's falling and rotating at the same time. Sweet little question, huh? So then G is equal to 3/2 A. So A is equal to 2/3 the acceleration due to gravity. Which, if you use 10, you get about 6.7 meters per second squared. Now, how could you find the tension in the cord? You plug it back in. Very good. So the tension was equal to mg minus ma. So then the mass of the object was 0.16. I used 10 minus the mass of the object, 0.16, and then the acceleration I just found 6.7, and I got 0.528 newtons.